So we are going to continue to talk about the colligative properties. Every year in the local and in the national program, there will be one question, one multiple choice with the colligative properties. First, let's talk about the concept. What is the meaning of colligative? Because this word is not so commonly used in daily life. Actually, it means number dependent. So colligative properties depends only on the number of the particles, or you can just say the number of particles, but not on the species. Of the particles. Basically, we do not care is A or B, but we care how many, right, of the solute particles in an ideal solution. We don't want to talk too much about what is the ideal solution. Similar to the ideal gas law or ideal gas, if you don't know what is ideal, you can just suppose it is ideal, okay? So there are a few stuff. Last time we already have a conclusion. So the vapor pressure of a solution will be lower than the vapor pressure of the pure solvent. I hope you still have this in mind. The equation is here. The vapor pressure of the solution is lower than the vapor pressure of the pure solvent. How to interpret this? We provided the equation, but how to interpret it is lower? Can we say, except the regular intermolecular forces among the solvent molecules? So in the solution, there is some extra intermolecular forces between the solvent molecules with the solute, right? Because you add some solute in the system, so there will be some extra interaction which will make the solvent molecules harder to vaporize. So this is why its vapor pressure will be slightly lower. So the more solute particles you put in the solution, the more decreased of the vapor pressure. So this is why we have the proportional relationship, the Raoult's law, right? Does this make sense to you? Good. So because the vapor pressure of the solution is lower than the solvent, and then we will get some conclusion. The first one is called boiling point elevation. Basically, the solution will have a slightly higher vapor pressure, boiling point than the pure solvent. For example, if pure water boils at 100 degrees Celsius, and then let's say the glucose solution, glucose equals the boiling point will be 100 degrees Celsius plus a delta X. The delta X is positive, which means the boiling point is slightly higher. And then the increment of the delta T, or the delta T is the increment of the boiling point, is proportional to the molality of the solute. And then the coefficient is a constant called Kb. It is called molar boiling point elevation constant. Basically means when the molality of the solute is 1 m, 1 m means it's 1 mole of solute dissolved in 1 kilogram of pure solvent. And then in this case, the delta T, the value will be just Kb. So this is the meaning of the Kb, a constant, which is characteristic of the solvent, right? So it depends on the solvent, but it not depends on the molality. It not depends on the temperature. Could you please also recall why we need to use molality rather than molarity here? Any idea why we introduce a new concept of molality? Why we do not just use the molarity already learned? There is temperature change involved, right? So if there's temperature, if we still use molarity, molarity is mole per liter. The volume of the solution is dependent on the temperature. So which means the molarity itself will change with temperature. This is not something we need. We want to simplify the system, right? So this is why we use molarity. Okay, so I think this equation is quite similar to the equation for vapor pressure, right? But how to interpret this? So we need to use a diagram like this. So the red line means, let me show you. This is temperature, the x-axis. This is pressure, the y-axis. So this part will be the gas, I think. Oh, wait a second. Yeah, this is the gas. At higher temperature and low pressure is gas. This is the liquid. So the red line is the equilibrium between the liquid and the gas. So if the atmospheric is 1 atm, so when at this point, at this temperature, this will be the normal boiling point of water, right? Because that is the equilibrium between the liquid and the gas at the normal pressure, the atmospheric pressure. But we know the vapor pressure of the solution is the blue line. Based on our previous discussion, it should be lower, right? So it needs to have a higher temperature to reach the same external atmospheric pressure, right? So this is why there will be a boiling point elevation. There will be a delta TB. Maybe we can add a B here as a suffix. The B means is boiling point, right? Delta TB. So I think this is called phase diagram. We are going to talk about this a little bit more in depth later. So based on the phase diagram, we can have a good understanding about why the boiling point will be elevated, right? Make sense to you? So similarly, if we have a look at the freezing point, so the freezing point, the original freezing point is here because this part is solid. Freezing means from liquid to solid is here, right? And then for the solution, the red line previously is here because the red line is the pure water or the pure solvent. So they meet here, which means this is the temperature to make the solid and liquid at equilibrium state. That is the freezing point, right? So since the solutions line is like this, is lower, so the new equilibrium point change to here, so as you can see, the freezing point actually is lower. So that is something we are going to discuss next page, but I think it's quite, similar. It's quite similar. So if we use another word, another sentence to try to interpret the elevation of the boiling point, the decrease of the freezing point is like this. So you have some solute particles in the system. The solute particles will produce an extra intermolecular forces to the solvent molecule, which will make the solvent molecules hard to vaporize, which will make the temperature higher to reach the same atmospheric pressure. So this is why boiling point is elevated. And in terms of the freezing point, you add some impurity in the pure solvent. So the solvent gets harder to crystallize because it's kind of, it's not pure anymore, right? So the solute particles, interfere the crystallization of the solvent in the mixture. So this is why it needs to cool down to an even lower temperature to crystallize. This is called the freezing point depression. So similarly, we also have a equation, so delta T of the freezing point, or we can say the depression of the freezing point, is proportional to the molality of the solute. And there is also a constant called Kf. This is also characteristic to the solvent. Is also, when the molality is 1m, and then the delta Tf equals to Kf, right? So quite similar to the boiling point elevation. So I will give you maybe 2 to 3 minutes for you to quickly finish these two examples. I think there are two, goals for these two practice problems. The first one is for you to be a little bit more familiar with the definition of molality. Another one is to apply these two equations. Is the molar mass of glucose 180.0 gram per mole? Okay, great. So we don't need to check it anymore. Oh, we need to calculate molar mass. Sorry, I misguided you guys. My bad. So if you finish, you can check with me. We don't need to use this. Do you have any different opinion regarding this question? Because I took a while, to show all of the work, but what I need to remind you is the significant figures. The idea should be clear. So you know the delta TB, you know the KB, right? So which means you should be able to figure out what is the molality of the solution. So the 100 should have infinite significant figures. right? Because 100 is kind of a constant. So you got the molality has only two significant figures. Both are determined by the 0.34 and also by the 0.51. And the unit will be mole per kilogram, because degrees Celsius are all cancelled. So you flip this, right? Kilogram per mole change into mole per kilogram. This is the correct unit for molality, right? Good. Yeah, let me know if you have any question. And then we can just express the molality, right? It should be the mass divided by the molar mass, right? Or you can use a different way. So we suppose the M, the uppercase of M is the molar mass, and then we need to divide it by the mass of the solvent into kilogram, right? We need to express into kilogram. So the 150.0 should be expressed into kilogram. So with some simple calculation, you should be able to get it 180. But in order to express, there are only two significant figures. We do not just write down 180, because 180 is not very clear in terms of the significant figures. If you put a dot here, it means it has 3. So if you want to express 2, you need to use scientific notation. So this is a little bit more details you need to pay attention. So 3 parts. First, how to express the molality. Second, how to use the equation, right? The boiling point elevation. Lastly, how to take care of the significant figures. Any question about these 3 points?
I have a quick question.
Mm-hmm.
So why did you do the second part? Like if you get 0.67 mole per kg, why is that not the answer?
You need to get the molar mass of glucose, but the M, the lowercase of m, is the
Okay.
molality, right? So you
Yeah.
need one more step, right?
Okay. Yeah.
Okay. So if you're good, we will skip the second integrative example because it's quite similar, right? And I also got some suggestion from you guys, so you guys probably can take care of those examples by yourself. I think it makes sense. Okay. So let me know if you have any question. Okay. So we have a very brief summary. So the presence of solute lowers the freezing point of a solvent. If the solute is non-volatile, the boiling point is also raised. So basically 2 parts, right? Boiling point up, freezing point down. So the freezing point depression can be used to calculate the molar mass of the solute. This is actually the example we just saw, right? If the solute is an electrolyte, this is something you guys need to pay attention. For example, if it's sodium chloride, if it's calcium chloride, right, they are electrolyte. So the extent of the dissociation or deprotonation must also be taken into account. What does it mean? Because we are counting the particle molality, which means if you have 1 mole per kilogram of sodium chloride, actually it will change into 1 mole of sodium plus and 1 mole of chloride. So which means the molality of the particles is 2 mole per kilogram, right? This is something you need to pay attention, right? Because we do not have any sodium chloride in the solution. Sodium chloride is completely dissociated. Make sense to you? Okay, guys, let's have a quick look of this question. You need to pay attention to the dissociation, okay? Yeah, we do have a tight time, but I want to ensure all of you have a good understanding. So if you have any question, please let me know, okay? For this question, you don't need to use the calculator because all of the molar masses are comparable, right? So this is for you to have a quick estimation. You suppose all of their molar masses are the same. So the difference is related to how many moles of ions it can produce. So there's another related question you may think about. Does this kind of hydrated water matter here? They probably will make the solution slightly diluted, right? But think about in total, there is only 20 grams of the solid of the salts, but there is 200 grams of water. So I think this is not the major factor. Okay, I have to stop here. We got most of your votes. If you can, figure it out in a few seconds, I probably will be able to show your answer. Great, thank you. Have a look. So we got two different answers, A and D. What is the special, property of A? I didn't see any difference between A and B, right? Because they are both A1, B1 type of electrolyte, right? So which means each mole of the compound will dissociate into 2 mole of ions, right? So the correct answer should be D, because each mole can dissociate into 3 mole, right? Does this make sense to you? So this is why, this is the major factor. Although the molar mass is slightly different, the amount of water is slightly different. But with our calculation, I think we should be able to conclude the number of ions produced will be the major factor, right? Lowest means it has the highest molality of ions, right? Make sense?
But I have a question.
Yeah.
Doesn't it mean like if it is in 5 moles of H2O, wouldn't it be like more solute in this copper sulfate solution than in the sodium sulfate, because has double the water?
The water will make the solute more diluted, right?
Mm-hmm.
But as I mentioned, in total, there's only 20 grams of salts, but there is 200 grams of water. So although they will give a different amount of water added to the 200 grams, but considering the total mass of all of those solids is 1/10 of the mass of the water, so definitely is negligible, right?
Oh, okay. Mm-hmm.
Mm-hmm. So that will not be the major factor here. So the major factor will be the number of ions produced in each case, right? Okay, one last thing I want to talk about is the application of the colligative properties in our daily life. So I think in the winter, some of you are in California, probably there are not so much snow, but like me, I live in New Jersey. So in the winter, typically there will be a lot of snow, right, in each winter. So you will see, people, spill some salts on the ground, on the street, right? That is used to prevent the freezing of the icing of the water on the street, right? Why adding salts can make this happen? Adding salts to the water will make the freezing point of water higher or lower.
It'll make it lower.
Yeah, and then, which means previously it will freeze at 0 degrees Celsius, and now it might need to be freezed at a much lower temperature, right? That means if the temperature now is that low, so the water will still be liquid. It will not be freeze, right? So we will, help the water to freeze at a lower temperature, which means it can keep liquid states at the regular temperature, let's say -5 degrees Celsius, right? So actually adding salts to the ice water is also an easy way for us to get a lower temperature. For example, if you add some calcium chloride to ice water or just to ice, you might get -15 degrees Celsius. So this is the easiest way for us to get a low temperature in the chemistry lab. Okay, let's continue. The last part of the colligative property is called osmotic pressure or osmosis. I believe all of you learned this part in biology. How many of you didn't learn this? Since you guys all turned your camera on, I couldn't get a very quick, idea from you guys. Let me ask Amelia, Tiffany, and Ashwa. Did you all learn osmosis from your biology class?
I'm doing biology this year.
Okay.
I did physics freshman year instead.
I see. Have you heard about osmosis?
Yeah, a little bit.
Okay. Yeah, we'll still have a quick discussion. So the general idea is like this. So if you have a U-shaped tube, and there will be a semi-permeable membrane in between the bottom in the middle. So the meaning of semi-permeable membrane is it can only allow the solvent molecule to pass, but it will prevent the solute particles to pass. So this is the meaning of the semi-permeable, right? Only some of the particles can go through it, but not the others. So basically, if this is the aqueous solution, water can, but the ions cannot, okay? Or the other, solute molecules or particles cannot. So if we add some pure solvent or just water in the left side and add some solution in the right side and keep the original height the same. So after a while, the results will be like this. Basically, the water side will be lower and the solution side will be higher. Why? Because the water side has a higher osmotic pressure. So it wants to dilute the solution. And the final goal is to reach equilibrium. When is equilibrium? Is when these two sides have the same concentration. But it can never be the same concentration since the left side is just pure water, right? So when the two sides is in balance, there will be a new pressure produced. So the height difference will produce a pressure to prevent the water molecules to keep flowing to the right side, right? So we call this, pressure into the osmotic pressure of the pure water. So we can say the pure water has a higher osmotic pressure. I should say the solution has a higher osmotic pressure than the pure water because the solution side, has a higher pressure right now, right? So this diagram uses a slightly different way to explain you the osmotic pressure. So we apply a pressure here to stop the osmosis and make the two sides have the same water level. So this pressure added will be the same as the pressure produced by this, solution column, right? Because it's the same idea. If you do not add the pressure, there will be a difference. If you add some pressure to keep them in the same level, so that level, that pressure you added will be the same as this high difference, right? So that is called osmotic pressure. So there is an equation related to the osmotic pressure. We use pi, uppercase of pi, to represent the osmotic pressure. It really doesn't matter which letter you use to represent the parameter, but this is a general idea. So it's related to the molarity. It's related to the R, the ideal gas law constant. It's also related to the temperature. So you don't have to memorize this equation, but you can keep this in mind. The osmotic pressure is proportional to the molarity. Because there's no temperature change, so this is why we can use molarity. We don't have to use molality anymore, right? Okay, so we can put it, the flow of solvent into the solution through the semi-permeable membrane is called the osmosis. So I think now you can have a quick look at about the diagram in the left side. It's quite similar. You have solution in the flask. The bottom is made by a semi-permeable membrane, and then you put it into the pure solvent, and then you will see initially the heights are the same, but at the equilibrium state, the heights are different. And then the pressure produced by the height difference is called osmotic pressure. Make sense to you? So let's have a look at the application of the osmotic pressure or osmosis. I think the first concept we need to know is isotonic solution. So if you need to get some glucose, right? Let's say sometimes you get sick. If you go to the doctor, and then probably sometimes you may need to get some glucose, right? Let's say you didn't, eat for a few meals, right? But we cannot just give you the glucose. We need to make sure the solution which is injected to your body has the same osmotic pressure with your body fluid. Otherwise, there will be some results like this. For example, this is the normal red cell, but if it put it into the pure water, not just say pure water or a more diluted solution, so the cell will expand. Does this make sense to you? Because the fluid in the cell is more concentrated. So the water will go through the cell membrane, which is a semi-permeable membrane, right? And then expand the cell. And finally, the cell will break. So this is very, serious, right? So if you, accidentally inject the water or, a more diluted, solution to your body, well, that would be very, very, very dangerous. But if you put, the normal cell into a very concentrated salt solution, the results will be like this, right? The result will be like this. So in biology, I believe you will learn something like this. If you put a plant cell in a very concentrated salt solution, because the plant cell has both the cell membrane and also the cell wall. The cell wall will not change the size or shape, but the cell membrane, let's say this is the wall, this is the membrane. The membrane will shrink, right? Because you put it into a more concentrated solution, so which means the water will come out. So there will be a separation between the cell wall and the cell membrane, right? What is this called in biology, guys? I think there should be a word to represent a situation like this? Do you guys know the word? Is it called plasmolysis? You didn't learn this yet? Yeah, it doesn't matter. No, just keep the word here for you guys to know. It's called plasmolysis. Plasmolysis, I should say. Basically, the separation of the cell wall and the cell membrane of plant cells when they are put into a more concentrated solution. Okay. Okay. There is something I think you guys can, read it by yourself. Dialysis. This is very common used, in I think in the hospital for the people who has issues with the kidney, right? You guys can, do some self-study. This is just the application of the osmosis. Okay, it's like, the artificial kidney. So we'll skip this part. Okay, the last part is the colligative properties for electrolyte solutions. We already talked about this, right? Because electrolytes can produce more particles. So there will be a factor I called Van 't Hoff factor. Basically, is for 1 mole of the electrolytes, how many moles of ions or particles it produces. So sodium chloride is 2. Makes sense, right? Potassium sulfate is 3. And for this iron 3 phosphate, it will be 5, right? No problem. But if you check this table, the observed value is always slightly smaller than the expected or the theoretical value for electrolytes. For non-electrolyte like glucose, it's just 1, so it's the same, right? But for all of the electrolytes, they are slightly smaller. So how to interpret this is called ion pairing. What does it mean? So in the electrolyte solution, the cations and the anions are not completely separated, not completely free. So the cation are kind of stick to the anion and pair, is not kind of closely, contact with, but it's still somehow not completely free, because each cation will be surrounded by a layer of water molecules. Each anion will also be surrounded by a layer of water molecules. This process is called hydration, right? I hope you can still understand what is the meaning of hydration. And we ask a question about the orientation of the water molecules surrounding the cation and the anion, right? There will be some differences. So, which means the cation and anion are still somehow stick to each other, but not, like in the solid sodium chloride or solid electrolyte, they're completely, closely contact with each other. So they are separated, but somehow they are kind of in a pairing relation. So this will decrease the total number of free moving ions. Does this make sense to you? Okay, so we finish, the first topic today. So the next 2 of the class today is gas and solid. So we'll talk about gas first. Did you all learn gas in your current, chemistry class? No matter it's, AP Chem or, what is the name? Not yet. Amelia, what kind of, chemistry class you are taking right now?
I'm doing AP Chem.
Oh, interesting. So I think last time we had a discussion, it seems like your school is using a different, sequence, right? Yeah, I think typically or normally, gas or gas law should be discussed, right now. Because if you just follow the AP Chem curriculum from Unit 1 to Unit 9, because gas is in Unit 3.
Yeah, my school does it differently.
Oh, wait a second. I think I need to unlock the meeting. We missed an Edward. I see, I see. Give me 1 second because I logged the meeting. Okay, let's wait. Just give me 1 minute. I need to make sure, Edward can be back. You guys can have a, very quick, read about, okay, great. Hello, Edward. Can you hear me? Edward?
Yeah.
Oh, great. Apologize. I locked the meeting. I didn't realize you you were disconnected. Do you have an estimation how many minutes you missed?
Like I'd say like 10 minutes, maybe.
Okay. I will send you the recording so you can find that 10 minutes to, make up, okay? Basically, we just discussed, the summary of the colligative properties, and also a little bit extension about the Van 't Hoff factor. It means, how many particles and 1 mole of electrolyte can produce. So you can, review the part after the class, okay? So we'll still move forward. Does this work for you? Okay, we'll continue, okay? So first, we want to briefly talk about, what is the definition of pressure? It's physics, but we want to, have a very brief look. So pressure is defined as the force divided by the area. So the unit is Newton over meter square. This is kind of a standard unit. So we call 1 Newton per meter square into 1 Pascal. So Pascal is the common used or a kind of a systematic unit for pressure. Although, in America, we use so many different, pressure units, right? Let me list a few. Probably you heard about some of them, might not be all of them. ATM, right? 1 ATM, 2 ATM. Bar, right? Anymore? PSI, right? So tire pressure is expressed in PSI. So if you have the experience to help your parents to pump, now you pump, right? To pump the tire, and then you will see the unit will be PSI. It's called pound per square inches. So this is a very, American way, right? Pounds, inch, right? This is something I can never figure out. PSI, anymore? Yeah, there might be a few. A millimeter of mercury, right? And a few more. So due to the historic reasons, we used so many different units. But you don't need to memorize all of them because in the test there will be a conversion factor to guide you. So no worry. And the most common used is Pascal, ATM, and bar, maybe millimeter mercury as well. So basically, the only one which is not so common is PSI probably, and also TOR, TORR, right? You probably will see different unit used in different applications. So the second question is, how is the gas pressure produced? How is the gas pressure produced? One keyword, guys. How? If we have to use one keyword, I will use collision. the pressure is produced by the collision of the gas particles with the wall of the container, right? This is how the gas pressure is produced. So there is a very straightforward, question. It's kind of a barometer in physics, a U-shaped tube, and then show you, the mercury in the tube. So let's be quick. Let's work on this question quickly, okay? So we are working on these multiple choices right now. I think, this question is related to physics. The key question is either you use the 615 to plus the 65 or to minus the 65, right? So keep this in mind. The pressure of the gas plus the pressure of this height difference equals to the pressure of the atmospheric pressure. Does this make sense to you? So that means the correct answer should be, should be C. So most of you figure it out. But this is not the normal atmospheric pressure because that one will be 760 millimeter of mercury, right? So this is much lower, so which means probably this U2, wow, interesting. This U2 is not put in Google, it's put in a high mountain, right? Because the pressure is much lower than it's supposed to be at the sea level, right? Okay, good. Most of you, figured out. So all of the pressures, let's have a quick look about the most commonly used. 1 atm is 760 millimeter of mercury, also called 760 torr. It is 101.325 Pascal, so it's 101.325 kilopascal. So I think that should be enough, right? Yeah, once again, you don't need to memorize those kind of stuff. You will be provided the values and the conversion factor. So next part is the ideal gas law. Ideal gas law was derived, based on the previous contributions from Boyle, Charles, Avogadro. So if you have a look at the constant temperature and the same amount of gas, so the volume is reversely proportional to the pressure. Basically means, let me give you a experimental, example to show you. If you have a balloon and then you put the balloon into the hot water, no, that is not the case. If you have a balloon and you use your hand to squeeze it, right? And then the balloon will reduce the size. That means higher pressure because you press it, means you increase the pressure, right? On the balloon, that means the volume will decrease. So P times V is a constant. Make sense? The second one, Charles, at the same pressure and the same amount of gas, the volume is proportional to the temperature. Basically means if you have a balloon, you put it in hot water, the balloon will expand because high temperature will make the volume increase. The last one, I think you can figure out by yourself. More gas will have a higher volume if the temperature and the pressure are the same. So there is a guy who is very smart, who is built kind of stand on the shoulder of all of those previous scientists, summarize a final equation, PV nRT, PV equals to nRT. It's called pivot. This is called the ideal gas law. So P, pressure, V, volume, and moles of gas molecules, R, a constant, T, temperature. So because, the P and V have different, units combination, but P have so many units, right? So the R may have different value with a different unit combination. So this box shows you all of the common used, R value and the constant. But there are a few stuff you need to really pay attention. First, temperature is always expressed in Kelvin. You cannot use degree Celsius, because if you use degree Celsius, this equation is not correct. So as you can see, all of them have Kelvin. And secondly, is here. So there is, these two has the same value, but a slight different unit. One is called kilopascal liter, another one is called joule. So I want to briefly show you some physics to guide you why 1 joule actually equals to 1 kilopascal times 1 liter, okay? So don't be scared by the physics, it's pretty straightforward. It's also fine if you couldn't, completely follow, okay? So 1 kilopascal is 1,000 pascal. 1 liter is 1 over 1,000 meter cubic. Does this make sense to you? 1 kilopascal, 1,000 pascal. 1 liter, because 1 liter is 1 decimeter square, not square, cubic, right? So 1 decimeter is 1/10 of 1 meter. So this is why it's 1 over 1,000, meter cubic. Basically, we can say 1 meter cubic is 1,000 liter. You are good? Okay, let's continue. So these two cancel. So we got Pascal times meter square times meter. I want to separate, the 3 times into 2 parts, because based on the definition of the pressure, as you can see, pressure times area will give you force, right? So which means this part will be 1 Newton. The circled part will be 1 Newton. And then it turned into 1 Newton times 1 meter. So the force times distance will give you the unit of work, which is joule. So just to give you a very brief, no matter it's review or, fresh about the unit, joule and the liter times kilopascal, okay? So keep this in mind. Sometimes if the joule is provided, you can write it down into liter times kilopascal. You can also write down into pascal times meter cubic. It's the same. Okay. Do you think you guys need to have a practice about how to apply the PV-nRT? Sure. If you never practiced before, guys, please do this by yourself after class. You must do it, because there are still a lot of tricks in applying this equation. A lot of things are very easy to be forgotten, right? So make sure you practice this problem. So what I want to talk is a very important experiment. This is somehow you probably couldn't get from self-study. The goal of this experiment is to measure the molar mass of a volatile liquid. The meaning of volatile means is easy to vaporize. So this is the goal of the experiment. So how can we achieve this? So first, I want to introduce the setup. You are going to have a hot plate, which can, heat a water bath. So some water is put into the beaker. This is the water bath. So the water will be, keeping in the boiling state, which means the water in the beaker will be 100 degrees Celsius. And then we are going to put a flask with the aluminum foil, cap the flask. And then you are going to put the unknown liquid with an unknown, molar mass in the flask. So next, basically, this is the setup. And also we have some tiny hole, maybe 1 or 2 tiny hole on the aluminum foil. Next, I'm going to introduce what kind of parameters we want to measure. The first one is called MI. Basically, is the mass of the empty flask plus the aluminum foil. Actually, when you measure the mass, I think you also measure the mass of the air, right, inside. Or maybe no, but it doesn't matter because later we still have the air inside, right? So let's skip this part. There's no air, but yeah, it doesn't matter. So this is the first parameter you need to measure. And then you will add some, liquid in the flask. And then you will put the flask with the aluminum foil cap in the water bath. And then turn on the hot plate and keep the water in the hot plate boiling. So since the water is so high in temperature, so the liquid will vaporize. And the vapor will squeeze all of the air inside and leave from the tiny hole. So finally, there will be a moment, so the whole flask is fulfilled by the vapor of the liquid. And then you continue to heat until all of the liquid is just gone. So at that point, it means in the flask, there is only the vapor of the liquid. And then we take the flask out and cool it down. And then the vapor will condense back into the liquid. And then at that time, we measure the mass of the final, which is the flask still empty, plus the aluminum, plus the mass of the liquid. Or I should say the condensed liquid, or the condensed vapor, right? Because the vapor is condensed into liquid. And then we get the delta M, which is MF equals to MI, which will be the mass of the vapor, right? Not equal, minus. Does this make sense to you? So far, so good, right? And next, we are going to use PV equals to nRT to solve the problem. First, what is the P? Is the atmospheric pressure, which can be read by a parameter, or you can just use 760 millimeter mercury, right? If the place you work on the lab is not too high in altitude, right? So let's say if I live in Princeton, New Jersey, I probably can just say it's 760, it's okay. But you can also use your phone to check the atmospheric pressure at your location, right? So you got the P. What will be the V? The V is the volume of the flask, because that is the volume of the vapor, right? What will be the R? Constant. What will be the T? This is the key question. I provide two options. The first, the temperature is the room temperature, and the second one is 100 degrees Celsius. Which one do you think should be the temperature used in the PVNRT? You are going to apply the PVNRT to the gas, to the vapor, right? So you want to get the temperature of the vapor. What's your idea, Amelia?
100.
It should be 100. So basically it should be 760 73 Kelvin, right? And finally is the N. So which means P is known, V is known, T is known, R is the constant. We can calculate the N. So basically we can know how many moles of vapor is in the flask when the liquid is just gone. And then you also know the mass. So if you know the mass, you know the moles. Can you calculate the molar mass? You can, right? So that is the general idea. That's the general idea. So finally, you can calculate the molar mass. So I have a question. So let's say if after our measurement, the mass of the vapor is around, let's say 0.4 gram. Let's suppose the condensed, vapor is 0.4 gram. So what should be the mass initially added in the flask? It should be exactly 0.4 or more than 0.4 or less than 0.4. This experiment is a little bit complicated, okay? So obviously, you need to add more than 0.4, right? Because you will have a lot of vapor actually escaped from the flask. But you don't want to add too much, because if you add too much, first, the experiment may take a much longer time to fully, for the liquid to fully evaporate it. And secondly, you waste your sample, right? You don't need to use so much. So let's say if 0.4 gram is actually needed, you may add, 1 gram, around 1 gram. So which means even there is some liquid, escaped, there still should be enough. But if you put less than 0.4, there will be a problem, which means even all of the liquid vaporized is still not enough to fulfill the flask. Do you have any question about this experiment?
I'm still confused about the 0.4 grams.
Oh, the 0.4 gram is just an example. If I suppose after my calculation, the mass of the vapor is 0.4 gram, because the mass of vapor finally will condense, change into the liquid, right? So my question is, initially, what is the mass of the liquid you need to add in the flask before you heat the flask?
Oh, so you'd add slightly more than 0.4.
Yeah, because if you add exactly 0.4, even less, the liquid is not enough to fulfill the flask, right? So which means when you design the experiment, you may need to do a kind of a rough calculation to make sure you add enough, but not add too much, right? Guys, can I give you, so can you have a quick, calculation to calculate in this case, in this question, what would be the minimum mass of the liquid you need to add, okay? What would be the minimum mass of the liquid? This question is very hard. So we are trying to figure out the first part, the initial part. So I know, in a lot of schools, with AP Chem offer, the teachers, barely offer experiment to students, or just do a few very simple experiment. But actually, this is not the AP curriculum. The AP actually requires around 10 big labs. It's called guided inquiry experiments. This is one of them, which is a pretty good one.
Do you need like more than 0.5 grams?
Where is 0.5 from?
Because there's 5 milliliters of liquid and it's at a molarity of 100.
But how can you convert this into 0.5 gram? You even have no idea about what the density of
Oh
the
wait,
liquid
I
is.
meant moles. Oh.
Uh-huh. So basically, here is you need to imagine the mass, and the mass equals to the moles times the mole mass. The mole mass is provided, so basically you need to get the moles, right? And the moles you can get from PV and RT, N equals to PV over RT. So I'm asking you to have a quick discussion about N. You know the P, you know the V, you know the R, you know the T. Guys, if you don't know the R, check it by yourself, okay? Do you have any question, Tiffany? Okay.
Why is the volume 125 milliliters if there's only like 5 milliliters of liquid?
This is a very good question. So the PVNRT is used to describe the gas, right? So the
Yeah.
gas actually is fulfilled in the flask. We are supposing the gas is fulfilled in the flask. So you don't use the 5 milliliter because this is the volume of the liquid. It doesn't work here. You need to get the volume of the gas, of the vapor, right?
Oh, okay. Mhm.
Mm-hmm. Does my work make sense to you? Guys, you don't have to follow my style to use the kilopascal and liter. Feel free to use 1 ATM, okay? Because the reason why I use this is because I can only memorize the 8.314 with this combination of unit, because 1 joule actually equals to kilopascal times liter. So if you use ATM or use other pressure unit, you need to figure out the value of the R by yourself. So I think, we already found 2 common made mistakes. The first one is the temperature is easy to be misunderstood into 25 degrees Celsius, the room temperature. The second one is Ashra asked, the volume should be the volume of the flask, is not the volume of the liquid, right? Actually, it doesn't matter how many milliliters of liquid you add, you just to make sure that enough than 0.4 gram, right? If you add more, it just will take a longer time. You need to heat there for a longer time and until all of the liquid is just gone. Guys, I have a question. Why we need to make sure, we catch that point when all of the liquid is just gone? let's say if we have some liquid left in the flask and then we stop the heating, how does this affect your results? It will make the molar mass you measured higher or lower. If we didn't wait until all of the liquid is just gone and leave some liquid left, and then we stop the heating, that means the mass of the vapor you measure will be higher than it's supposed to be, right? Because you have some liquid left. And then this will increase the mass, which means it will increase the moles, right? If you increase the moles, oh, wait a second, sorry. It will increase the mass, but the moles is still the same because it's calculated from PV/nRT, so the molar mass will be decreased, right? So you will underestimate the molar mass in that case. One more question. Why finally I only give one significant figure? It's because 100 has only one significant figure. 100.0 means 3, but 100 is just 1, because this is just an estimation, right? We don't know the exact molar mass. So if we say m is around 100, means the molar mass can be 0 to 200, right? Because plus and minus 1 is on here. So if you get the result in between 0 to 200, it should be, around 100. So this is why we got this. So a lot of students are also confused by another mass. So they also measure the mass when the liquid is initially added. Let's say the mass including the 5 milliliter of liquid. So is this mass useful? The mass of the flask plus the aluminum foil plus the 5 milliliter of liquid is not useful, right? Because that is not the mass of the vapor. What we want to get exactly is the mass of the vapor. Okay, we probably don't have time to finish this question, but I want to give you, another hint. So let's say here it asks you which one will produce the largest percentage of error in the molar mass. So how to calculate the percent error? The percent error is defined as the measured value minus the actual value divided by actual value minus the theoretical one divided by the theoretical one times 100. This is called error percent or percent error. So if this is the case, guys, have a look. If the balance is the top loading one, which means it can only measure to 0.01 gram, which means the actual value minus the theoretical value from the balance will be plus and minus 0.01. But the theoretical one is around 0.4. So this is why we need to calculate this 0.1, 0.4. So the error percent will be plus and minus 0.01 gram divided by 0.4 gram, which is around 2.5 or 25%. 2.5%. Yeah, right? You guys can help me check about the mass. And then if C, the flask has a plus and minus 1.0 milliliter, error, which means the error percent will be this divided by what is the theoretical value for the volume of the flask?
125.
Yeah, so you can calculate the results by yourself. And then you can do something similar to B and D, and you should be figure out which one has the largest percentage error. This question is pretty hard. This is one of the most difficult questions I have ever seen in the local exam, at least for the descriptive and the laboratory parts. So we can easily change this into an error analysis question, because there will be so many stuff we can access. Okay, guys, you probably need to do some review for this experiment. If you have a chance to work on the lab in your school, that would be the best, because this is, experiment can be discussed in this way, but without, the hands-on experience, it's still not enough. Okay. Obviously, we cannot do it here. Guys, let's have a 4 minutes break. We'll restart at 9:25. Okay. See you later. Okay, let's start.
Dr. Shen,
Yes, sure.
what was the answer to the last question that we just did?
Ah, great. Let me see. Let me have a quick look. I would like to say
I chose
it
D,
D.
but
I think
D.
it's A, right? Because for D, plus and minus 0.2 degrees Celsius equals to plus and minus 0.2 Kelvin. But you need to divide it by 373 Kelvin, right?
Oh, okay. So yeah,
The-
it'd be A.
Yeah, don't divide it just by the 100 degrees Celsius, because in the equation PV and RT you need to use Kelvin, right? I think probably the answer is A. I didn't really do the calculation very carefully, but it seems like the top loading balance is a big issue here. But you guys can double check. But this is from the local 2012. You can find the answer by yourself. Okay. Thanks for asking, Ashraf. Which means you didn't take a break, right? you have worked on the question. Okay. Next part, the gas density versus the molar mass. We want to figure out what the relationship between the density and the molar mass. So we need to do some mass derivation. So density equals to mass over volume, right? Molar mass equals to mass over moles over N, right? So, and then we have PV equals to nRT. So we want to use the PV and RT to connect the density and the molar mass. So let's try. So first, I will change the N into the molar mass. So PV equals to M over molar mass. I hope you guys can follow, okay? So I will stop a while after each step for you guys to take notes and also digest the contents. I don't know how comfortable you feel about the derivations like this. So we got this. So now put the molar mass in the left side. So we got M equals to mass over volume times RT over P. So I did a two-step. The molar mass is to the left side, the volume is to the right side, and the pressure is also to the right side. But I put the volume here because I need to use the M over V. That is the density, right? So finally, we got the molar mass equals to the density times RT over P. So why I want to derive an equation like this? Because I can conclude now, at the same temperature and the pressure, the molar mass is proportional to the density, or the density is proportional to the molar mass. Why this is important? And I think now you can understand why carbon dioxide will have a higher density, a higher fraction at the lower place. I think I read a story when I was a child, I think. So it's kind of a father, a dad, kind of bring his kids to a very weird place, maybe with the dog as well. And then the dog, died, and the kids and the father is okay. And then they realize finally they figure out the dog is died because the carbon dioxide in the air the dog breathes, and that level is too high. What does it mean? Which means the carbon dioxide actually kind of sink to the lower altitude. That's because it has a higher density than the nitrogen gas, than the oxygen gas. Why it has a higher density? Because the molar mass of the carbon dioxide is higher than nitrogen, than oxygen, right? So if you want to, collect some gas, let's say if you want to collect the carbon dioxide gas, you have two ways. You have a tube, and then you put the gas here, or you have a tube, you put the gas here. So they are called air displacement method. It's basically you use the carbon dioxide to displace some air and then make it a full-filled tube, right? So which one you will use based on the density difference of the air and the carbon dioxide? Since we already know carbon dioxide has a higher molar mass than air, this is a little bit tricky because air is a mixture. Theoretically, there is no molar mass for air, right? But we can calculate the average molar mass of the air. But air is mainly composed by nitrogen gas and oxygen gas. One is 28, another one is 32 in molar mass, right? So which means the average molar mass of the air is definitely in between 28 and 32, which are both smaller than 44, the molar mass of carbon dioxide. Based on this equation, we can conclude the carbon dioxide has a higher density, so which means the right method is better because the carbon dioxide will prefer to sink in the bottom and squeeze the air out. If you do it this way, the carbon dioxide will sink, so which means you will get some impure carbon dioxide, right? Does this make sense to you? Okay, great. So I will leave this question for you to try, which is related to the relationship between the density and the molar mass, okay? And then is a very quick introduction about the STP, the molar volume at STP, which is called the standard molar volume. Molar volume means the volume of 1 mole of gas. So at STP, which means 0 degrees Celsius and 1 atm, the molar volume, the standard molar volume is 22.4 liter per mole. Guys, do the calculation by yourself because Vm equals to V over N equals to, based on PVNRT, V over N equals to RT over P. So you can put the value, the ATM, the 0 degrees Celsius in to get the 22.4, okay? Okay, great. So we'll continue. So partial pressure. Partial pressure is basically, if you have a mixture of several gases, so the total pressure is the sum of the partial pressure of each gas. This is the definition. So what is the meaning of 21% of E? Unfortunately, my pen is running out of battery. Let me see. This is not. Let me try to use my finger, but it's probably not as good as my pen. So the 21% actually is the volume percentage. But obviously we know it doesn't mean the air has a corner. The 21% of the volume is oxygen gas. Another 78% of the volume is nitrogen gas, because both of the O2 and N2 will occupy the whole space, right? So this 21% actually is the mole fraction. Is the mole fraction. Basically, in 100, molecules of the air, you have 21 particles or 21 molecules of O2. You have 78 molecules of N2, and you have in total 1 molecules of other gases, right? So which means if the atmospheric pressure is 1 atm, what will be the partial pressure of the O2? That will be 0.21 atm, right? Does this make sense to you? So which means we can we can conclude the partial pressure of a certain gas I equals to the total pressure PT multiplied by the mole fraction of the gas I, right? I think it makes sense, right? You guys can derive this equation by using PV nRT by yourself, because they have the same T, they have the same V, so the pressure will be proportional to the mole. So you got this, right? So the application of the partial pressure in chemistry is mainly related to the water displacement method to collect a gas. Basically, we bubble the gas into a upside down, test tube or container with water filled, and then the bubbles will displace the water, and finally you collect the gas in the top, because the gas definitely has a much lower density than the water, so it will go up, right? But the pressure here is not only contributed by the gas you need. It also have the water vapor, right? So which means when you use PV nRT to calculate how many moles of the gas you got, you need to use the total pressure to minus the vapor pressure of water. So this is this AP question. So let's have a quick look, okay? So we decompose ethanol into ethane and water, and the ethane is not soluble in water, so it can be connected in the test tube. So you have the total volume is here, the pressure is here, the temperature is here, the vapor pressure of water is here. I'll give you 30 seconds for you to have a quick analysis of how to calculate the moles of the C2H4, which is the ethane. You don't need to calculate the final results, just figure out what is the equation. So what I want to remind you is when you use the P, make sure you minus the vapor pressure of water from the total pressure 0.822 atm. But since the vapor pressure is expressed in a different unit, so this is why you may need to convert the unit of the torr into the atm, or you convert the atm into torr. It's up to you, right? But you need to do the unit conversion, and then you multiply by the volume, and then you divide it by the temperature and the R. Does this method make sense to you? Okay, great. Guys, I will have to use the very limited response I got from the student who showed the video. So which means if you turn your video on, I have no idea about how you think about the question. So I will have to continue, okay? Okay, so the answer is here, guys. Try this as your homework. The next part is the KMT, which is called kinetic molecular theory. And then there is another law called Graham's law. What does this mean? So basically for the gas molecules or a gas, we have a few assumptions to apply the kinetic molecular theory. The first one, we suppose the gas molecules are like spheres. And secondly, we suppose the distance among the gas molecules are far away from each other, which means we can ignore the size of the molecule itself. The third point is we also ignore the intermolecular forces among the gas molecules. And lastly, we suppose their collision are completely elastic, which means there is no energy loss during the collision. So let me briefly write it down. The first one is gas molecules are like spheres. I will just write down in this way since I did not have my pen. The second one is the distance is much greater than the radius. I should say, let's say the size of the molecule are negligible. So we can ignore the size because the distance is much greater than the size. The third one is the IMF can also be ignored since they are so far away from each other. The last one is the collision is elastic, which means when they collide with each other, there is no energy loss. You probably can ignore the last part because it's very physics. So with all of those four assumptions in mind, we need to give you a very important conclusion is the kinetic energy of a gas molecule or of a gas is proportional to the temperature expressed in Kelvin. Kinetic energy is proportional to the temperature, no matter what is the type of the gas. Basically, two gases, if they are different, if they have the same temperature, the kinetic energy of these two gases are the same. So this is the first point. The second one is the distribution of the molecular speeds. So basically, for a gas, not all of the gas molecules have the same speed. There will be a distribution. For example, here, the x-axis is the speed. The y-axis is the relative number of the molecules with a certain speed. So as you can see, at a certain temperature for a certain gas, it's like this. What can we conclude? Basically, there will be a few molecules with a large speed, a few molecules with a very small speed, but the majority of the molecules have a kind of, medium speed, right? So I think this is kind of natural, right? Not all of the molecules actually have the same speed. So when we say the kinetic energy, we are talking about the average speed because kinetic energy equals to 1/2 times the mass times the speed squared. This is pure physics, okay? This is the definition of kinetic energy. Ke equals to 1/2 mv squared. Is someone disconnected? I heard a sound. Yeah, Ashur is gone. Okay, I think the meeting is unlocked, so he should be able to get back if he wants. Okay, we will continue. So let's have a look at the other gases. This is the O2. This is, this is O2 at the same temperature with the H2. So if you observe the red line with the blue line, not this red line, okay, is the top red line. What's the difference? Did you see that? What can we conclude about the average speed? Which gas has a higher average speed?
Oh, the hydrogen is higher.
The hydrogen, right? The average is around here, and the oxygen is around here. So how can we interpret this? We can do it this way, because they are having the same temperature, which means these two gases will have the same kinetic energy. Hello, Ashwa, welcome back. So if the kinetic energy is the same, which means the speed actually is inversely proportional to the mass. And obviously, oxygen gas has a larger molar mass, which means each molecule of O2 is heavier than the molecule of H2, right? So this is why it has a lower, speed. Does this make sense to you? Is this natural? Basically, a heavy guy moves slower, right? A heavy molecule, a heavy gas molecule moves slower. So we want to, derive this equation. I think it's on the next page, which is here, which is the Graham's law. So it said the rate of effusion of a gas, basically the speed, we don't need to make it too complicated, is inversely proportional to the square root of its molar mass. How can we get this? So Ke equals to Ke. So 1/2 m1 v1 square equals to 1/2 m2 v2 square. Oh, they are at the same temperature, okay? Definitely at the same temperature. So this is why they have the same kinetic energy. So now we can say m1 times v1 square equals to m2 times v2 square, because the mass is proportional to the molar mass, right? And then we can say m1 over m2 equals to v2 over v1 square. So finally, we can say v2 over v1 equals to m1 over m2 square root. So this is exactly the word description about Graham's law. It's the same idea, right? Heavier, slower. Lighter, faster, right? But it's not, directly related. There is a square root relationship, right? So I have a question for you guys to think here. So there is a long tube. So in the left side, you have some cotton with some ammonia solution, concentrated ammonia. In the right side, you have some cotton with some concentrated hydrochloric acid. So both of these two solutions are very volatile, which means it will produce the ammonia gas from the left side and the HCl gas from the right side. And these two gases will, will effuse through the tube, and then they will meet in a certain place. But when they meet, they will react to produce the ammonium chloride solid. This is acid-base neutralization. Make sense? These two are gases because they are molecules. The last one is a solid because it's ionic, right? It has an ionic bond. So this is why it is a solid. So what can we observe? Because it is a white solid, so we will see a white ring, on a certain place of the inner wall of the long tube. So based on the location of this white ring, we can confirm the Graham's law, right? Guys, have a look. Does the position here make sense to you? It's closer to the HCl and further away from the ammonia. Yes? No? HCl has a molar mass of 36.5. Ammonia has a molar mass of 17. So the lighter ammonia moves faster. So it will travel a long distance, right? Make sense to you? Okay. Let me see. Oh, I think we already talked about the last part, right? Temperature is proportional to the kinetic energy. Or kinetic energy is proportional to the kinetic energy, I should say. Because temperature actually determines the kinetic energy. So I would like to revise this part into EK is proportional to T, okay? Rather than T is proportional to EK, because we need to figure out what is the reason, what is the results. Okay, if you guys have no question, we will continue. So let's have a quick look at this example. I will give you all of the molar mass. CH4 is 16, helium is 4, 32, 64. I think it's correct. Okay, let's use 1 minute. Maybe you guys can be faster. Please pay attention. The temperature actually is different, okay? The temperature is different, which means the kinetic energy is not the same. The kinetic energy of the gas we need to find is 4 times of the kinetic energy of CH4, right? If we suppose CH4 is gas number 1, those options are gas number 2. So we should say M2 V2 square equals to 4 times M1 V1 square. I think you guys are very close to the answer, right? Do you have more votes submitted? Since they have the same speed, right? So which means the molar mass of the second gas should be 4 times of the first gas, right? So I think the answer is already clear. The answer is C. So we got 2 students who chose A. So you need to be careful, right? A is just 1/4 of the molar mass. So you guys may need to derive the equation by using the kinetic energy relationship. Be careful. This is very easy to make mistakes. I think you also have another easy way for you to interpret. So a higher temperature, which means the molecule can move faster. So this is why you need to choose a heavier molecule, right? Because the heavy molecule at the same temperature will move slower. And right now, because the temperature is higher, so it will move slightly faster, which can be the same as the molecule with a lower molar mass at a lower temperature, right? Okay, any question? If no, I think we have the last part for the gas part, which is what is the difference of the real gas with the ideal gas? So the assumption of the ideal gas has 2 major points. The first one is ignore the size. The second one, ignore the IMF, right? But actually, not all of the gases at all of situations can ignore both of these 2 factors. So there's a question, under what conditions the real gas behaves more like and ideal gas. I think we discussed this before, right? Temperature should be high, right? To make the molecule move faster, to make the distance further. And then we can ignore the size, we can ignore the IMF. The pressure should be low, right? Because pressure is low, the volume is large, and then the particles are far away from each other, right? So under this kind of situation, the real gas behave more like ideal gas. So finally, let's have a look at the real gas law, which is here. What does it mean? So the contents in the parentheses is the theoretical pressure. The contents in the parentheses of the right side is the theoretical, or you can say the ideal. I would like to use the ideal because we are talking about real and ideal. Ideal. So the pressure here and the volume here are the real pressure and the real volume. So based on this equation, we can say the real pressure is smaller than the ideal pressure, and the real volume is greater than the ideal volume, right? Does this make sense? Real pressure is smaller than ideal pressure. It's because one keyword, the existence of IMF decrease the frequency of the gas molecule to collide with the wall, right? So this is why the pressure is decreased. Does this make sense to you? And then for the right part, that is the contribution of the size of the molecules itself, right? Because if you cannot ignore the molecule itself, the real volume will be greater than the ideal volume, right? So you got an equation like this. So there will be no question to assess you how to apply this equation, but there will be question to assess your understanding about the difference between the real pressure and the ideal pressure, the difference between the real volume and the ideal volume, okay? Oh, there is a question here. We already answered the first one, okay? So there is another one. Which one is more likely to be ideal, ammonia or helium, guys?
I think helium,
Why do you think it's helium?
because it's smaller, so it has less volume.
Is that exactly what we need for ideal gas? The size is smaller, which means we can easily ignore the size, right? If you consider the size difference or the size comparison, ammonia definitely is greater in size than helium, right? So which means from this perspective, the volume factor in ammonia situation, in ammonia, is harder to be ignored. How about IMF? Which one has a higher IMF? Definitely ammonia, right? Ammonia has hydrogen bonds. It's polar. It's a larger molecule. So both the London dispersion forces and dipole-dipole interaction in ammonia is greater than that in helium, right? So this is why the ammonia is less ideal. Helium is more ideal. Both the IMF and the size, right, kind of works from the same direction. Okay, guys. Now doing this way is 10 o'clock. So we will use around 10 more minutes to finish the phase diagram, which means we will leave the last part, the solid. which might need another, I think, 30 to 40 minutes. So let me think about this. We have one more class, and then in that class, actually, we also have a lot of content to cover. So I can either, make a video by myself without student and share the video with you, which I will kind of cover the topic 5, the solids, right? Or let me decide in this way, okay? I need to see your submission about the final test to decide what is the best way. If I didn't get any submission, that means I will use the last class to finish, part 5 first, which means because I don't know what's your feedback, right? So although I probably will still choose some question to discuss, but probably we don't need to use so much time. How do you think? Do you have any suggestion or idea about this? It's not because, we got any issue in, teaching the class materials. I think it's just because, I'm a little bit too ambitious. I put too much stuff in the lecture notes, right? Maybe next if we have the next year, I probably will slightly revise the contents. If I want to give you the best, give you the most, but sometimes it didn't work in that way. Any suggestion? If no, I will choose, the way I like. But no worry, I will, cover this part, no matter it's from a video or it's from, the last class. Good. Okay. If you guys need to leave, it's okay. We'll use around 10 minutes to finish, the phase diagram, and then you can get the recording from me if you missed the last part. Okay. Phase diagram, I think, is not very complicated. The phase diagram is a diagram like this. The x-axis is always the temperature. The y-axis is the pressure. Actually, already saw the phase diagram when we discussed the colligative properties, right? So can we figure out, what is the stage of these 3, areas by yourself? Solid, liquid, and gas. I think this is very straightforward. At high temperature and low pressure is gas, right? And at high pressure and low temperature is solid, right? So something in between is liquid. So the lines are the equilibrium lines, which means that is the equilibrium between the 2 phases. But there is a very special point, which is called triple point. That is the existence or the equilibrium of all of the 3 states. So we answered the first question, right? And then there are a few, questions. Let's have a read. The first one is if the temperature is raised from 50K to 400K at a pressure of 1 atm, which is from here to here, right? The substance boils at approximately 180, oh, sorry, not, it's from 50, it's from here to here. Made a mistake. And then it said the substance, I don't know which stuff, okay. The substance boils at approximately 185 Kelvin. Is this correct? Boil means liquid to gas. This is liquid, this is gas. So which means we need to find this point, right? Rather than this point. So it's wrong, right? The liquid phase of this substance cannot exist under conditions of 2 atm at any temperature. So if it's 2 atm, can we find the liquid? We can, right? The liquid is here. So this is also incorrect. The triple point occurs at approximately 165 K. This is correct, right? The next one, at a pressure of 1.5 atm, the melting point of the substance is approximately 370 K. Let's raise, and then let's have a look. It's around here, right? 1.5 atm. So the freezing point or the melting point will be here. Solid to liquid, right? I think this is incorrect, right? Because it's in between 200 and 300, right? Let me know if I make any mistake because I'm using my finger. Sometimes it affects me. Last one, the critical point occurs at approximately 1.7 atm and 410 K. We didn't talk about the critical point yet, but anyway, it should be this point. The point here is called critical point. We are going to talk about critical point later, okay? Is this correct? Around 1.7 and 410? Yes, right? Okay, let me see. What do I have the... Yeah, let's talk about the critical point first. So in any phase diagram, there will be a critical point on the line between the liquid and the vapor. What does it mean? The critical point is made by a critical temperature and a critical pressure. So the temperature at and above which vapor cannot be condensed to liquid, no matter how high the pressure is. How high the pressure? This temperature is called critical temperature. What does it mean? So which means, there will be a minimum temperature. If you want to condense the vapor into liquid by increase the pressure, there will be a minimum temperature. If the temperature is higher than this value, no matter how you increase the pressure, you cannot condense the vapor. So this is called the critical temperature. So similarly, we can, define the critical pressure, which means there will be a, limitation of the pressure. If the pressure is lower than this value, and let me see, higher than this value, no matter how you lower down the temperature, you cannot condense the vapor, right? It's quite similar. So combining the critical temperature and the critical pressure, we got the critical point. So at this range, which means when the T is higher than the critical temperature, when the P is higher than the critical pressure, this area is not gas anymore, it's not liquid anymore, it's called a new phase, called supercritical fluid. Supercritical fluid is not gas, it's not liquid, it's not a mixture of gas and liquid. It's a new phase, it's a totally new phase. So we started to learn solid, liquid, and gas from elementary school, but finally we learned the fourth phase. And actually there is another phase called plasma. You probably learned from physics, right? So there are a bunch of phases, not only S, L, and G, okay? So this is called supercritical fluid. It's a new one. It has both the character of the liquid and the gas, but it's not liquid, it's not gas, okay? This is called the supercritical fluid. I have a question. Although our time is limited, but I want you, to deepen your understanding. So why there is a critical temperature? So we increase the pressure, we want to condense the liquid, but there will be a minimum temperature to prevent the pressure increasement to condense the vapor. why there is a minimum temperature like this? Why, if the temperature is higher than this, no matter how we increase the pressure, I cannot condense the vapor anymore? Increase the pressure to condense the vapor is to overcome the basic IMF, right? The fundamental IMF. So guys, I will leave this question for you to think, okay? So why there is, the critical temperature and the critical pressure here? If a gas has a higher critical temperature or a higher critical pressure, what does it mean? Is it related to the IMF? Is it related to the volume of the gas molecules itself? Think about this. And then we want to have a look at a few examples of phase diagram. The first one is the phase diagram of water. The second one is the phase diagram of the carbon dioxide. Let's start from the carbon dioxide one, because from this one, we want to discuss the sublimation. What is sublimation? Solid directly change into gas without going through the liquid, right? Let's have a look. This is 5.1 atm. So if we suppose this dash line, the D dash line is 1 atm, which means the carbon dioxide solid will directly change into the gas without going through the liquid, right? This is sublimation, right? The reason why carbon dioxide or dry ice can sublime is because the triple point is higher than 1 atm, right? If a substance with a triple point higher than 1 atm, we can say this species can sublime, right, at atmospheric pressure. So obviously we know water cannot sublime. Why? Because 1 atm is here, but sorry guys, the triple point is here. So which means if you go through 1 atm to the right side, first solid will change into liquid and then finally into gas. This is the normal change, right? This is different from the carbon dioxide. But what is the special property of the phase diagram of water? If you have a look at the slope of the solid liquid line, so you probably see the slope here is negative, but the slope here is positive. What is this about? This is related to the thermal expansion. What does it mean? So if we fix the temperature, let's say this line, the FH line, fix the temperature and increase the pressure. So for carbon dioxide, it will change liquid into solid, right? Which means the solid is more condensed than liquid, or we can say the solid has a higher density than liquid, because increased pressure will, squeeze the species, right? Decrease the distance among the molecules, right? So if you increase the pressure, the density will be higher. So from here, we can say the density of the solid is higher than the density of the liquid. This is normal for most of the species. This is called thermal expansion, right? Most of the species have thermal expansion. Increase temperature, it will increase the size. But if you have a look at this line here, the EG line in water, fix the same temperature, increase the pressure, will change solid into liquid, which means the density of the liquid is greater than the density of the solid. This is the uniqueness, one of the uniquenesses of water, right? It's not thermal expansion. So, to conclusion, how can we conclude whether species can sublime, whether a species has kind of the unique, density of solid and liquid? So you know where to observe in the phase diagram, right? Okay, great. And then finally, yeah, we'll leave the example question for you to try. Finally, let's have a look at the phase diagram with multiple triple points. This is sulfur. So you see gas, liquid, not surprising, but you see two different types of solids. One is called rhombic, another called monoclinic. So basically it means there are two types of sulfur solid, two different crystals. So you can see there will be two triple point. One triple point is here, right? Another triple point is here, right? Here we can also call it a triple point because triple point is defined as three phases. So phase is slightly different from states. What difference? States means solid, gas, liquid. But phase means if they are different in property, they are called phase, which means if you mix two different types of solid, there are two phases there. For example, if you add water to carbon tetrachloride, because these two liquids are immiscible, so which means they will have two different layers. So if we analyze the number of states, we should say one state because they are both liquid. But if you analyze the number of phases, they are called two phases because the top part are not the same as the second part. So this is the difference between the phase and the states, okay? Okay, guys, let's take maybe 1 or 2 minutes to finish the last practice problem, which is from the local 2020. Yeah, you guys are pretty fast. I didn't finish the reading. No rush. Okay, I got 5 votes. Do we have more? I think the results are already very representative. So most of you choose C. C actually is correct. The rhombic sulfur is denser than the monoclinic. How do we know? You draw a line here, right? So which means increase the pressure will change the monoclinic to the rhombic. That means the rhombic is denser, right? Make sense? Let's have a look at A. The rhombic sulfur cannot be sublimed without first converting to monoclinic. Actually, it can. If you draw a line here, it can direct it into the gas. So if we say the rhombic sulfur cannot be sublimed without first converting to monoclinic sulfur at 1 atm, this might be correct. But if at 1 atm, the monoclinic one cannot sublimate as well, right? There's no way for it to, skip the liquid. So it didn't mention the pressure here, although by default, we talk about 1 atm. But here, I think we need to argue the pressure is not necessary to be 1 atm. So this is why option A is incorrect. Any question about phase diagram? So we leave one practice problem here. We leave a extended question about the deeper understanding of critical temperature and the critical pressure to you guys. Oh, there is another question. Okay, great. I really appreciate your participation, in the extended time. Hopefully I didn't, affect your dinner. I know some of you in California, so what the time? 3 hours difference, right? So that means it's 7 p.m. So probably that is the dinner time. Okay, guys, let's stop here. So I will show you the final test, which is around 2 to 3 hours to you. Definitely by Tuesday. Hopefully you guys can find a 2 hours of chunk during the holiday and finish it and submit before our next class. If you can submit by Saturday, that would be the best. I can still take some time on Sunday morning to grade your work, and then I can get a sense which questions, which topics we need to review in a deeper way or in a better way. Okay. Alex, do you have any other stuff to update?
Yeah. Today's the last day to sign up for season 2. So, yeah. If you are still planning on signing up, please do so soon. That's all.
Great, thank you. And if you already signed up, make sure you have the payment as soon as possible, because we are going to start the season 2 in 2 weeks, right?
Yeah.
The exam will cover part 5. But not many questions, because we use around 20 hours, 18 hours in total to cover so much content. But if we squeeze all of the content into a 2-hour test, so probably there will only be one question or a few small questions related to part 5. Okay, thank you guys. Yeah, sure, Alex. Can we restart a new meeting? Okay, great. We'll see you guys. Oh, by the way, on Friday night, we'll have a session for the molecular orbital theory. If you can make it, join the link. I will share the link with you. It will be a new link, because I'm going to make that one live in YouTube. Okay. If you cannot, it's fine. I will share you the recording later. Okay. That's related to molecular orbital theories, the part we skipped. Okay. See you. Bye-bye. Happy Thanksgiving in advance.
Thank you. Bye.
Bye-bye.